recording. Okay, so we're going to take a look at Module 1 and get started on that this evening. So as we look at Module 1, you're going to notice that we're going to be studying linear and curvilinear motion and kinematics. This, for the most part, should be review, okay? Even though you've had these things in previous classes, it's going to be things that we're going to be kind of continuing to go back to throughout the term. So I really want to make sure that we have a good, solid understanding and a review of the concepts here. So as we look at our learning plan, you're going to notice that we have a part 1 and a part 2 of PowerPoint presentations. So we'll be looking at the first one this evening and then kind of transitioning over the next times that we're together to part 2. And then you're going to notice here that it says, read the following sections in chapter 11 of your ebook from McGraw-Hill. When I say read, I kind of loosely say that, but I encourage you to use that as a learning activity, okay? Am I going to, quiz you on what's in the book? No. Okay, in terms of like the reading. No, I'm not going to do that. But it does help to more deeply explain some of these concepts that I'll be reviewing and going over, but it gives you a really good explanation there. So these are the sections that we're going to be covering in chapter 11 of your textbook, okay? We're also going to be completing the example problems that you see here during class. So these are your practice problems, okay, that we're going to be going over. So through, I want to say, 2 and about a half lectures or times that we're together, we'll be going through these elements, okay? And then once we're done with all of that, you'll be submitting the practice problems and the application problems. So for grade. The session recordings, as I said here, I'll be populating these lectures after I, go through them at night, and you will see the links to the YouTube videos populated here in the spring 2026. The last year's videos are going to be listed down below, okay? So if you did want to reference those are there for you. And then you're going to notice that we have our practice problems. Again, just another list of the elements or the sample problems and the examples we're going to be going over from the book. And then, and they'll be doing those together in class. And then the application problems. There are 10 application problems, okay? And each one of those are listed in the bold here, and those are going to be found throughout the chapter. How the book works is they'll go over some things, and then they're going to assign problems that relate to the information immediately ahead of that. And then it'll do some more. It'll expand a little bit more, and then it'll have another set of problems. So they're going to be kind of sprinkled throughout the book. So those are the numbers that we see here. The information immediately below is going to be final answers, as well as any notes that I might want to put there as far as handing in. Okay, so those are going to be 10 problems that you'll be handing in for the Module 1 application problems. Okay, on the calendar, you're going to find the due date, and then also that additional 7-day grace period. Okay, and then once we get closer to working on those, we'll check the calendar on those. All right, so let me go back to the learning plan, and I'm going to open up the PowerPoint presentation here. I just got to scooch this up a little bit. And we will kind of start going through things. So in a chapter 11 here, and I know it kind of feels weird to start it in chapter 11, but the full book is actually a statics and a dynamics book, with the first 10 chapters focusing on statics. And then the second chapters are 11 and going to the end are going to be focusing on dynamics. Now, at the beginning of the chapter here, we talk about, it kind of explains that dynamics is really a combination of both kinematics and what they call kinetics. Okay, and I'm going to go down here. Kinematics, as we know, is the study of motion without worrying about forces or how those forces occur, interact with a mechanism. Okay, so last term, when we had kinematics, we were just we did look at velocities, accelerations, displacements, but we weren't worried about, how the elements as a design are going to be functioning when we have forces and masses and things that are going to be pushing around with them, okay? And as we had said in kinematics, it's the first step, if you would, in the design process. So now what we're going to do is we're going to kind of add on to that, All right. And that adding on is what we call kinetics. Kinetics is going to be the relationship between the forces that are acting on the bodies, the masses that are present, and now that they're moving, how do they affect things? Okay. So that's the study of dynamics. That's the study of dynamics. So it's adding on. Now, when we look here in chapter 11, we're going to be focusing on rectilinear motion, which is straight line motion, and that's going to be the first stuff that we look at here tonight and a little bit the next time that we're together. And then we're also going to be looking at curvilinear motion, and this is going to be things that are, going to be going around a curve or things like projectiles. Okay, so we'll be covering those things here in our first module. So starting with rectilinear motion. When we have rectilinear motion, to fully define that motion, so motion just means it's moving, okay? And to fully define motion, we need to know where it's located, okay, what its distance is, what its position is. We need to know how fast it's going, velocity. And then if that velocity is changing, what is the acceleration, okay? And by noting those three things, we can fully define the motion, which I know you've done, along the way. I've done some of this with you. So when we look at position coordinate, that's going to be defined by either a positive or a negative value with respect to an origin. So we need to know, first of all, where are we starting? Where's our origin? And then what are we going to consider positive? Okay, so we're going to have, usually if we're in a horizontal rectilinear motion, going to the right in the X direction is positive. Going to the left would be negative. Okay. If it's up, that's most often positive. Going down is going to be negative. But you can always change that convention by defining it at the beginning of a problem. So if you're finding, oh, all of our stuff is going to the left, instead of dealing with all negative numbers, you can say going to the left is positive. Does that make sense? Okay. So defining where something is, its origin, and then knowing if it's going in a positive or a negative direction is going to be important. Now, motion of that particle is known if the position coordinate for that particle is known for every value of time. So in terms of position, we want to know, okay, if it's moving, all right, it has motion, then if I'm 2 seconds or 8 seconds into that motion, where is it? Okay, that's fully defining that position. Now, once we kind of know what's happening with the motion, we can also graph it based on an expression or an equation that is going to fully define that, position. Okay, so we're going to find that we're going to be using Excel to create a curve that is going to represent how the position changed over time for that particle. Okay. The next thing that we use to further define motion is going to be how fast it's going. What is its velocity? Okay. Now, velocity can be in terms of average velocity or instantaneous velocity. Average velocity is when we look at we've covered a large distance over an amount of time. Okay. And so what was the average? So for instance, if we travel in a car for an hour and we look at from the start to the finish where we covered 60 miles in 1 hour. Okay. We would say that the average speed or velocity was 60 miles in an hour. All right. But now does that mean, or it doesn't mean that you were going a steady 60 miles an hour for a full hour? Okay. What you were doing is probably starting and stopping, but by the time you got done, you covered 60 miles in an hour on average. That's how fast you were going. Okay. Instantaneous velocity, on the other hand, is when we look at any given instant in time, how fast am I going? So if I'm in my car and I look down at my speedometer, instantaneously, right now, I'm going 70 miles per hour, 60 miles per hour, 30 miles per hour, whatever it might be. Okay. Now, instantaneous velocity can be positive or negative, okay, depending on direction. Velocity is a vector. So based on that direction, we can define if it's positive or negative. So that again would be set by a convention that we would define at the beginning of a problem, okay? Now, to determine the equation to define the motion or the velocity portion of the motion, we would take the first derivative of the position. Okay, and you've probably done that in physics class. How many have done that where they've done a derivative? Yep. Okay, so we're going to be practicing that, refreshing that again. And once we know that equation of that line that represents the velocity, now we can also plot what that looks like and then determine at any given instant in time, how fast are we going? Okay. And then the third element that kind of finishes out or rounds out fully defining the motion is looking at acceleration. Acceleration is going to be how fast velocity is changing. Okay, so when I'm speeding up or I'm slowing down, if we're in a car, for instance, we can feel acceleration. Okay, if I'm going at a steady rate, it doesn't feel like I'm moving at all unless I'm looking out my windows, right? So if I am accelerating, I can feel it. Now, if I'm speeding up or slowing down, that's an acceleration, okay, or a deceleration. But I can also change direction, and that's an acceleration. Like when I go around a corner, okay, that's an acceleration. Even if you're going at a constant velocity around that corner, you're constantly changing direction, which means that you're accelerating. Okay. So to get acceleration, it is going to be a derivative of the velocity equation, okay, of the motion. So then we're gonna do one more derivative and then we can get to the acceleration. Okay. So if we start with a position, which is very common for some of the problems we're going to be doing, we do a first derivative, a second derivative, and we get that velocity and that acceleration equation so that we can create then a curve that's going to represent what's happening with the acceleration. Concept quiz. What is true about kinematics of a particle? So the first statement says here that the velocity of particle is always positive. Is that a true statement? It is not a true statement, right? Because again, that's going to depend on the direction it's going, and it can go in a negative direction. So that wouldn't be true. The second statement here says that the velocity of a particle is equal to the slope of the position line of a graph, of the position line graph. Is that true? It's got potential. It's got potential. So just like all multiple choice problems, let's read the last two and see where those fall. If the position of a particle is 0, then its velocity must be 0. That's false, right? Because depending on where the origin is, we might be just crossing over an origin, right? And if that's 0, that doesn't mean that we're not moving. So yeah, the velocity doesn't have to be 0. And then the last statement here says, if the velocity of a particle is 0, then its acceleration must be 0. When can we have something that the velocity is 0, then it could still be accelerating? Anybody have any examples where that could be true?
You're slowing down your car. Or you're just starting your car.
Or you're just starting your car? Yep. There's one more kind of classic example we'll see in an example a little bit later, but it's when, for instance, we throw a ball up in the air and it gets to the top, the tippy top of, how high it's going to go. There's still gravity or acceleration acting on it, but at that very tippy top, it's not moving, right? It's changing direction. So the velocity can be 0, but it still has an acceleration on it. So that would be an example. So it looks like B was our correct statement, and indeed that is very true. Okay. So the first problem we're going to be looking at here is going to be a concept application problem. This is not a practice problem, but I'm going to demonstrate it for you and kind of show you how we're going to be using Excel to solve a problem like this. Okay, so what I'm going to do is I am going to actually go underneath my camera and we're going to look at this problem. This is on page 622 in your textbook. It's concept application 11.1. Okay. And what it has here, it says, consider a particle moving in a straight line and assume that its position is defined by x is equal to 6t squared minus t cubed. Okay. So this is the equation for the line that is going to define the position of a point with respect to time. Okay, so that's the value. So it says what they want us to do then, it says where t is in seconds and x is in meters. We then want to take it a step further and define what the velocity would be. Okay, now to do that, as we said earlier, we would take the first derivative of that position equation. So you'll notice here that our velocity is going to be equal to dx over dt. And then what happens is they get this 12t minus 3t squared. So to do that, a derivative, we're going to use that power rule. We're going to take 2, which is the power of the t, times 12, or I'm sorry, times 6 to get 12. And then we're going to subtract 1 from the power, okay? And then that goes to t. So 12t is taking the derivative of the 6t squared, okay? Minus, and then we're going to do the very same thing for the next variable. So we're going to take 3 times a 1 that's out here, right? So that's going to be 3 out front, t, and then the power is going to be minus 1, so it's going to be t squared. So now this is equal to our equation to define the velocity with respect to time, okay? And then we do that one more time, one more derivative to get the equation for acceleration. So this is going to be the, we're going to take dv, or the velocity divided by the time. And we are then going to take 12 to the power of 1 times 12, I'm sorry, 12t to the, and t to the power of 1 times 12 is going to be 12. And then because this goes to a minus 1, 1 minus 1 is equal to 0. So there we lose the t after the 12. And then we're going to say minus 2 times 3, which is 6. And then the 2 minus the 1 just goes to a t. So now this is going to equal the acceleration equation for our curve. And we're going to use those 3 equations to create the 3 curves that we see here. The top one is for position, the second one is for velocity, and the third one is for acceleration. Now, how can we use these in Excel? Well, if I go over to Excel, you're going to notice here that I have pulled up the Chapter 11 Concept Application 11.1. I have 1, 2, 3, 4 tabs underneath here. I'm going to look first at my position tab. This is going to be the chart and the columns here with the data to represent the equation for the line that defines where the position is over, in this case, 6 seconds. Okay, so the first column here is going to be my time, 0 through 6. The second column is going to be the distance, the x, if you would, because in this case, I guess they're referencing a horizontal. So it's going to start here at the distance at time 1, time 2, time 0, 1, 2, and so on all the way to 6. Now, to find what the distance is at the given time, we're now going to program the cells with the equation that they gave us in the problem. So you're going to notice here that if we look back underneath, the equation for the position was x is equal to, so for that x column, we're going to say, all right, that's going to be equal to 6 times the time squared minus the time cubed. So if we go back to Excel, okay, I'm going to zoom in here just a little bit. You're going to notice that in this cell, I know it's hard for those who are virtual or even in the classroom to see my function here, so I pulled it out. Oopsie. I pulled it out just so that we could see the value. So this is going to be equal to 6 times A2. A2 is the cell here for the time, squared, so it has the caret 2 there, minus A2, which is the time, cubed, okay, caret 3. So that's what's programmed in here, and then it's dragged all the way down so that we get our values of what is the distance for each one of these increments in time. Then once we have those increments in time and we have the x's programmed, we're going to use those 2 columns to create the chart of the graph. To do that, And it might be something if you haven't done, Excel in a little while, we are going to go back in. We are going to select the two columns, not the heading, just the two columns. We're going to insert a chart. Now, you might know the type of chart that you want, so you can select it over here, but I like to just grab onto recommended charts, and then they're going to give you some options, and I like to kind of see like, oh, okay, which one looks best. So I'm just going to grab this one down here. I think it's the third one from the top for mine. I'm going to hit OK. And now you're going to notice that it creates this generic chart for me. I'm going to kind of scooch it over here. Now, when I have my chart, what I need to do is I need to give it a title. All right, so this is going to be, and you can see here, it's going to be distance versus time. Okay. And then I also need to, I'm just going to kind of put this in the middle here, label my axes. Right now, they're not labeled. So all you do is you select the chart, and then there's a plus sign here. If you click on the plus sign, you just want to check axis titles. And if you hover over any of these without actually selecting them, it'll kind of give you a preview of what it would be. So we just want to add axis titles. And then now you're going to change by double clicking the title here. And it's just like a regular, like editing, anything. So it's going to be X, and then this one is feet are the units. Make sure you put the variable with the units in both cases. So the X would be going vertically. The time would be going horizontally. Okay. And then there is your chart. All right. It's that simple. All right. If you need help with that, let me know. You're going to be creating one like this. You don't have to do that right now. I'm just kind of demonstrating for the time being. So that's your first chart for position. All right. Then you're going to notice that there's a second tab for velocity. So if I go over there, same type of format. First column is going to be your time. Second column is going to be our velocity. We're going to program the velocity column items to represent the equation for the velocity. Okay. And then the time is going to be referenced in that first column. Okay. Once we have our two columns here, we're going to select again, insert, and then recommend a chart. Again, mine is the third one from the bottom. And then once you have that, it'll then plot the chart here, and then you'll have to make those adjustments with giving it a title and then putting the axis titles on as well as the units. Okay. And then the third tab that you see here is for acceleration. And again, same thing. We've got our time, we've got our acceleration column. The cells are going to be programmed with the equation for acceleration, so the 12 minus 6t. And if we go back here, then the chart over on the right-hand side is going to be representative of the two columns, time and acceleration. And then you just want to add the labels and change the items that we see here. Okay. Now, you're going to notice that I also have one extra tab. Okay. The last tab that I have here, the very first one actually, is going to be the time. Okay. Now, what this does for us is this is kind of a review of the problem. The top here, you're going to notice that each one of the equations for position, velocity, and acceleration for, in this case, the concept application 11.1 are listed up here on top. Okay. Then down here on the bottom, we are going to find, not on this particular problem, but on problems that we're going to have coming, is sometimes we want to know what is the velocity when the time is 0. Okay, because it might not always happen on an even increment or an even second. So we want to know exactly where that is. And depending on the form that either the velocity, or if we want to find what the time is when the distance is 0, or the acceleration, depending on the form, if the form is in that quadratic form where you've got a square and just a regular variable, then you need to use the quadratic equation to solve for when the times would be 0. Okay. And you probably remember that, but this is going to, and you can do it manually if you like to do it manually, but this is just a little calculator defining the A, B, and the C for each one of the variables here. And then it calculates for us when we cross over that 0. Okay. And then these would be the times 0 in this case and -4 when we would get those values for 0. So that's there as an extra. It's not asking for us to do that in this particular problem. It just wants us to create the curves for the position, velocity, and acceleration. Okay. Now, again, this is just to demonstrate or show you what we're going to be doing on the next two examples, which are sample 11.1 and sample 11.2. And then at that time, for those examples, you're going to be building the Excel spreadsheet. Okay, so this is just kind of a warm-up. So any questions on that concept application and using Excel to create these three curves, motion curves? Okay. So what I'm going to do is, this is kind of a nice little spot to stop. We're going to take our break, and then we'll come back and we'll continue on with our first, if you would, official sample problem / practice problem. And then we'll look at creating this Excel spreadsheet together. Okay. So I am going to stop our recording.